Hey everyone. Today in class we talked about continuity. We went over what continuity means. We talked about what it means from a limit standpoint, from an algebra standpoint. We also talked about what it meant from a graph standpoint. And then we learned some results, things like polynomials are continuous, algebraic functions, trig functions, exponential functions, log functions. These are continuous on their domain, things like this. Also, if you add functions or subtract them or multiply them or divide functions that are continuous, you get continuous functions, except for the one little thing where you get division by zero. So we talked about all those results, but the next couple examples that I'm going to do, if you think of this continuity definition as kind of like a story, then these next couple examples kind of come before, they're earlier in the story than when I gave you those results. Okay, so I want you to pretend that you haven't heard those results yet, that like polynomials are continuous everywhere, things like this. And look at these examples first. And then from these next couple of examples, we're like, okay, well, we can generalize this to all polynomials are continuous, that kind of thing. All right, so let's look at this first example here. Okay, so again, we said in class that algebraic functions are continuous on their domain, and everyone agrees that the domain of square root of x is 0 to infinity with a bracket on the 0. So everyone would then agree that this function is continuous on 0 to infinity. You can also see from a graph that that's true. But again, let's try to ignore the result that, for the moment, that algebraic functions are continuous on their domain. I want to prove to you that this function is continuous on the interval 0 to infinity with a bracket on the 0. Okay, first of all, what does it mean if I say it's continuous on this interval here? What does it mean? It means the function is fully continuous at every positive number, like 1, 2, 7, even decimals like 2.59, pi, things like this. And any positive number at all, it's fully continuous. And then what's the story with 0? Because we have a bracket there, it means it's not fully continuous at 0, but it's continuous from the right at 0. Okay, so from scratch, if I don't want to use a result, if I just want to from scratch prove to you that this is continuous on that interval, 0 to infinity, then it's going to take some work. The first thing I'm going to do is I'm going to prove to you that it's continuous at every positive number. Okay, how many positive numbers are there? There's infinitely many positive numbers. So when I showed you how to prove that a function is continuous at a number, there were 3 steps. Remember, you would have to first check if the limit of the function exists at the number, then can you plug the number into the function, and do those two things equal? So there's a 3-step process to prove the function's continuous. But if I want to prove the function is continuous at every positive number, you can't just start picking positive numbers, like say, okay, we'll prove that it's continuous at 1, then later on at 2, then later on at 7, then at 2.58. When are we going to stop if we do this? This would take a 3-step procedure. This would take another 3-step procedure. This would take another 3-step procedure. This would take another 3-step procedure. Even if you do 100 calculations like this, you're not going to be able to prove that it's continuous at every positive number, because there's more than 100 positive numbers. There's infinitely many positive numbers. Okay, so what I'm going to do is I'm going to show you a trick that is useful in math that you'll see every once in a while that helps you prove something is true for infinitely many numbers by doing one calculation. So it's a really important trick. So the idea is going to be, I'm not going to tell you the number. What I'm going to do is I'm going to call the number that we're going to find we're going to check to see if this function is continuous at the number a. A is going to stand for a positive number, but I'm not going to tell you what it is. Okay, so that's the idea. Instead of saying I'm going to show you this is continuous at 2, I'm going to say let a be a positive number, but that's all I'm going to tell you about it. And if I can prove to you that the function is continuous at a, and all I tell you is that the a is a positive number, then it must be true for any positive number because I didn't specify which one it was. So if I say let a be some positive number, and I prove to you that it's continuous, fully continuous at a, then it's fully continuous at any positive number at all. That's the idea. So that's a really neat trick if you understand it. So here's how we're going to do it. So first, I'm going to prove that f is continuous on the open interval 0 to infinity. In other words, I'm going to deal with 0 later. So here what I'm saying is I want to prove to you that it's continuous at every positive number all at once. So again, the way you're going to do it is you're not going to tell me what the number is. So we'll call it a. So you say let a be a positive number. But again, I haven't told you which one it is. So I'm telling you that a is greater than 0. That's all I'm telling you about a. Once again, if I can prove from here that the function is continuous at a without ever telling you anything more about a, except for the fact that it must be positive, then this function must be continuous at any positive number. Okay, so now how do I prove that the function is continuous at a? You go through that 3-step procedure we talked about. The first step, you ask yourself this question: does the limit as x goes to a of f of x exist? All right, so let's try to calculate it. I know it's a little weird if we don't know a, but we're going to be able to calculate it anyway. The limit as x goes to a of f of x is the limit as x goes to a of square root of x. Now, what do we know about the limit of square root of x? We know that to take the limit of any algebraic function, you can plug in, as long as you don't get division by 0. There's no division here, so we're good with that. You don't get a negative inside of a root. You won't get a negative inside of a root because a is not negative. You won't get, and as long as you don't get 0 inside of a root, and a is not 0 either. So we can go ahead and plug in. For any positive number, we can plug in. You get square root of a. Square root of a makes total sense because a is a positive number. You can have it inside the root. So this is the limit, so it exists. Okay, so the answer is yes to the first question. Does the limit exist as x goes to a? Yes. And you see, we use the limit law there. This limit law, when we went from here to here, okay, that was a limit law. And that's true no matter what a is. So I don't have to know what it is. It's true as long as a is a positive number. No matter what a is, as long as it's a positive number. All right, what's the second step in proving that it's continuous at a? So the second step is, does f of a exist? In other words, can you plug in a to the function? And the answer is yes, because if you try to plug in a, you get square root of a, and this is not undefined or anything because a is a positive number. You're allowed to have a positive number inside of a square root, so the answer is yes. And the third step was, did the two answers equal each other? The answer for step 1, the limit answer, is it equal to f of a? In other words, does the limit as x goes to a of f of x equal f of a? And the answer is yes. And the reason is because they're both equal to square root of a. Right? The limit is square root of a, f of a is square root of a. They both exist, they're equal. So what's the conclusion? Kind of ran out of room, I'll write it here in purple. So f is continuous at a. I'm talking about fully continuous. And so this means, so f is continuous at any positive number. If you're wondering how I'm making the jump from a to any positive number, it's like this. The 3 steps I just proved here. It's true. If remember, I told you a is a positive number. That's all I told you. So it must be true for every positive number. Think about it like this. What you can do now is, if you're wondering if it's continuous at the number 5, you can change every a in what I've written to 5, and everything works perfectly. If you want to know, okay, well, is it continuous at pi now? You change every single thing that I've written here, every single a to what I say, pi, to pi, and everything will work out perfectly, and it'll be continuous at pi. So that's the idea. One more time. If you want to prove something's true for infinitely many numbers, in this case, I want to prove that this function is continuous at every positive number, you say let a be a positive number, but that's all you tell me about it. And with only knowing that information, if you can prove that it's continuous at a, then it's continuous at every positive number. Okay, so we're almost done. We've shown everything except for what's going on at 0. So now I need to show you that it's continuous at 0 from the right. So that's what we're going to do now. Okay, so now I want to show that f is continuous from the right at 0. So we're going to do another 3-step calculation. I'm going to ask 3 questions. First question is, does limit. Now this limit's going to be a right-hand limit. Limit as x goes to 0 from the right of the function exists. It's a right-hand limit because I want to know if it's continuous from the right. Okay, and the answer is going to be yes. Here's the calculation you do. You do limit as x goes to 0 from the right of the function is limit as x goes to 0 from the right of square root of x. And we've talked about how you can plug in to find this limit. Or you can think of a graph, but remember I said you can plug into an algebraic expression as long as you don't get 0 inside of a root, or negative inside of a root, or division by 0. Here we do get here we do get a 0 inside of an even root. But it's okay because if you're on the right side of 0 the whole time, you never get a negative. The idea is if you get 0 inside of a root, sometimes the actual limit might not exist because you'll end up with negatives inside of a root depending on what side you're on. But because x is approaching 0 from the right, x is always a positive number. So if you imagine trying to figure out this limit from a table, you would never be plugging in a negative number into the root. So then everything is okay. So you can go ahead and plug in this time. And you get square root of 0, which is 0. So this limit does exist. So the answer is yes. This limit exists. Okay, next question. In other words, can I plug in 0 to the function? Does f of 0 exist? The answer is yes to that, because if you try to do that, try to plug in 0, you get f of 0 is square root of 0, which is fine. You get 0. So the answer is yes. And did we get the same answer? So for step 3, does the right-hand limit as x goes to 0 of the function equal what you get when you plug in 0? And the answer is yes, because this answer here was 0. This answer here was 0. So yes to this question. So what did we learn from this? So f is continuous from the right-hand limit from the right at 0. Okay, so f is continuous at every positive number, fully continuous, and it's continuous from the right at 0. So that means it's continuous on 0 to infinity. Maybe I should write that down. So let me erase a little more. Okay, so now just to conclude it here, since f is fully continuous on 0 to infinity, so it's fully continuous at any positive number, and f is continuous from the right at 0, f is continuous on the closed interval, well, bracket 0, comma infinity. Okay, the only other thing to really say here, I mean, I basically proved what I was supposed to prove, but you might say, well, what about all the other numbers? You know, is this everywhere where it's continuous? Which is what I'm trying to show you, is this is everywhere where it's continuous. Well, basically here's the deal. What numbers have I not looked at? Well, we haven't looked at 0 actually from the left side, but you know that the limit as x goes to 0 from the left of this function doesn't exist because this function, you can't plug in negative numbers to this function, so that limit can't exist. Or another way to say it is there's no graph on the left side of 0 for square root of x, so the left-hand limit doesn't exist. So it's not fully continuous at 0. And then what about negative numbers? Well, remember there's a 3-step thing you would have to check. The second step says, can you plug the number into the function? And you can't plug in any negative numbers into the function. So it can't be continuous at any negative number. So it's not continuous at any negative number. It's not continuous at 0 from the left. So this is exactly all the places where it's continuous. All right, so we just learned that square root of x is continuous on the closed interval 0 to infinity. And as a lead-in to the result that we'll see in a few minutes, and that we already saw in class, notice that 0 to infinity is also the domain of square root of x. So at least in this example, that function there is continuous on its domain. Okay, let's go ahead and look at another example. This is going to be one more example where we practice doing infinitely many calculations all at once. It says, prove that this function is continuous on negative infinity to infinity. Again, this is part of the story, so you have to imagine this is before I mentioned to you that polynomials are all continuous everywhere. If you already knew that, then what is there to show here? You just quote a result. But if I haven't shown you the result yet, because we're not at that part of the story, then how would you prove Or another way to say it, how do you prove from scratch that this function is continuous on negative infinity to infinity? Well, how many numbers are there from negative infinity to infinity? The answer is infinitely many numbers. So how do I prove them? How do I prove that this thing is continuous at infinitely many different numbers? You can't do infinitely many different calculations. So use a trick. The trick is you're going to say, let A be a number in here. So A is a number in there. But I'm not going to tell you anything else about the number. So it's just some number in there. So basically A stands for some number, and I don't know what number it is at all. And then if I can prove to you that the function is continuous at A without ever telling you what A was, then it must be true that f is continuous at any number. Okay, so that's the idea. Let's go ahead and go through it. And we don't have to do separate calculations for this one because there's no places where it's continuous from the right, continuous from the left, where we might have to do a separate calculation. So this one's going to be just one calculation here. So I'm going to start off by saying let A be any real number. Or I could say let A be in negative infinity to infinity, which is the same thing because that's all real numbers in there. Okay, then I want to ask three questions. First, does the limit as x goes to A of this function exist? The idea is we're going to be using limit laws, things we learned about limits. So to check this, well, you do limit as x goes to A of f of x. That's limit as x goes to A of x squared plus 2x minus 5. And back in the limit law section, we said when you're finding the limit of a polynomial, you can always plug in. So we'll use that. You can break it down even further and use all the different limit laws and make this very long, but we already know that result from, a couple sections ago. So when you're taking the limit of a polynomial, you can just plug in. So you get a squared plus 2a minus 5. So this mess here is the limit. There's nothing wrong there. You don't have like a negative in square root or division by 0. You're squaring a, no problem. 2a, no problem. You're adding and subtracting stuff, no problem. So that is a number that exists. So yes, the limit does exist, and it's that thing I circled there. Second question is, does f of a exist? In other words, can you plug in a to the function? Or another way to say it is, if you don't tell me a, is there any problem plugging into the function? And I don't know what a is, but you can plug in anything to a polynomial. You don't have any issues. You don't have any negative inside of roots. You don't have any numbers that are not in the domain. So the answer is yes. F of a, you can just go ahead and plug it in. It's a squared plus 2a minus 5. So no problems there. The answer is yes. Third question is, did you get the same answer for both? In other words, did your limit answer equal your f of a answer? Does limit as x goes to a of f of x equal f of a? And the answer is yes, because both of these things, this limit and this, both equaled a squared plus 2a minus 5. That's a squared plus 2a minus 5. That's a squared plus 2a minus 5. So since all three answers are yes, the function is continuous at a. So f is continuous at a. And since a could have been anything, so f is continuous at any possible number. I'll just write negative infinity to infinity. Once again, understand the idea. I'm doing infinitely many calculations all at once by not telling you what the number is. If I just give you a number and I say, show it's continuous at 5, then you've only showed it's continuous at 5 and nowhere else. But if I don't tell you the number and I say, let's show it's continuous at a, and I don't tell you anything about the number, then it must be continuous at every possible number. Another way to think about it is that if you were going to show the function is continuous at 5, I kind of already did that, because you just take all this, okay, maybe not the first line there, but take everything after the first line, change every a, let's just go this much here, change every single a you see there to 5, and everything will work out perfectly. So we will have shown that f is continuous at 5. Now change any a to any number you want. Pick another number, 107. Change every a here to 107, and everything will work out fine. everything will work out fine because just knowing that a is a number and that's all we know, everything worked out fine. So I've done all the calculations, infinitely many calculations all at once for you. Okay, so that means it's continuous on all real numbers. And that's going to get us to the next example. I mean, to the result finally. But let's look at this real quick. F was a polynomial, and you see it's continuous at all real numbers. Also, you know the domain of a polynomial is all real numbers. So once again, this is leading into the result that's coming up, that this function is continuous on its domain. Okay, so example 4, I showed you we had an algebraic function there. It was just square root of x, it was an easy algebraic function, but it was an algebraic function. It turned out to be continuous on its domain. This is a polynomial, and this polynomial is continuous on its domain, and basically we generalize that result to all the typical functions that we see. So we get to this result here. Actually, we're going to get two results. Well, this result and then the one on the next slide. So first thing it says is that polynomials are continuous on all real numbers. Well, if you remember that the domain of any polynomial is all real numbers, then this is the same thing as saying polynomials are continuous on their domain. Okay, the next thing says rational function. I didn't do an example of a rational function, but same idea here. A rational function is continuous wherever it's defined, meaning on its domain. Okay, so polynomials are continuous on their domain. Rational functions are continuous on their domain. While we're at it, almost all the nice functions, as long as they're not complicated, like I'm only talking about simple functions. Like let's look at this next slide here. Any one of these types of functions are continuous on their domain. So that's what it says. The following types of functions are continuous at every number in their domain. So if you find the domain, you found exactly where they're continuous. All right, so what do we got? Polynomials, which is what the last slide said. Rational functions, which is what the last slide said. Okay, it says root functions here, but we can generalize that to algebraic functions. So this is any algebraic function. See, if it says root functions, they just mean square root of x, cube root of x, fourth root of x. But if you take something like square root of x plus 5 over 3x minus 2 square root of, or maybe cube root of x plus 1, whatever, make it an algebraic function, again, the same thing. You just have to find the domain, and you found where it's continuous. Okay, what else? Trig and inverse trig. Now again, when I say trig, I just mean sine x, sine x, cosine x, tangent x, secant x, cosecant x, and cotangent x. Nothing else. Like, I'm not talking about sine of cosine x or 5 times sine x. Just plain sine x, plain cosine x, and then their inverses. So just plain sine inverse, cosine inverse. Nothing else added in there. You don't have a couple of functions being added or multiplied or any combination like that. Just these simple functions. Then exponential functions, again, I'm only talking about things like e to the x, 2 to the x, not something like 2 to the power x plus 1, okay? And then log functions, and again, when I say log functions, I just mean log base a of x, so like log base 3 of x or natural log x, things like that. So what's the conclusion here? Polynomials, rational expressions, algebraic expressions, and elementary functions are all continuous on their domain. So if you find their domain, you found where they're continuous. Okay, so then what if you have something that's built from those, but it's not just those? Then we have this next result. The next result says that if you have two continuous functions, so f is a continuous function and g is a continuous function at the number a, let's say, then if you add them, it's also continuous at a. If you subtract them, it's also continuous at a. If you take one function and multiply it by a number, it's continuous at a. If you multiply two functions, it's going to be continuous at a. If you divide two functions, it's going to be continuous at a, unless, of course, you get division by 0 when you plug in a to g. Remember, when there's a division, there's always an extra issue. This result is only talking about one number at a, but it can be generalized to any interval. So, for example, if f and g are continuous on, let's say, 0 to 3, then if you add f plus g is continuous also. on 0 to 3. So this is how you deal with more complicated functions. You know, adding it by if you've got a function that's built up of adding, subtracting, multiplying, dividing, or a number in the front, you can argue that it's continuous from this result. We'll give you another quick one here. So if f and g are continuous on the interval -3 to 8, then if you divide them, this is continuous on, well, you have to change it a little bit. It's -3 to 8, except any numbers that cause division by 0. Any numbers that cause division by 0 if you plug them into G. Division by 0. So it might not be this where it's continuous. You might have to throw out some numbers. If, for example, the number 5 is a place where you get division by 0, like if you plug in 5 to G, you get division by 0, then you have to throw 5 out of there, for example. So if I ask you, for example, let me go ahead and erase some stuff real quick. So if I ask you, where is the function, let's just call the function f, but x squared plus 2 to the x, where is this continuous? This function is not a polynomial. It's not an elementary function. It's built up of a polynomial. This is a polynomial. This is an elementary function, or you can call it exponential function if you want to call it that. So we don't have any previous results that tells me about this function where it's continuous, but this theorem, theorem 4, will tell me where this is continuous. You'd have to argue like this. You'd say something like, okay, x squared is a polynomial, so it's continuous on its domain. That's from the previous slides, which is all real numbers, so it's continuous on all real numbers. 2 to the x is an exponential function. So from the last slide, it's continuous on its domain. And the domain of 2 to the x is also all real numbers. So by this theorem, if you add them, this is continuous on -3 to infinity. So you look at it in pieces and you say, okay, from the pieces, if you build this thing, and if you build a function by adding, subtracting, multiplying, dividing, or putting a number in front of a function, it's still going to be continuous at whatever interval you're talking about. Okay, so that function is continuous at -3 to infinity, but that's the kind of argument you'd have to make. Real quick, that was kind of fun. Let's do one more example kind of like that, maybe a little more complicated. Okay, so another question. So if I ask you, where is the function, let's call it g of x this time, g of x equal sine inverse x plus square root of x continuous. Okay, so it's basically going to go like this. Actually, maybe I shouldn't have put a plus. Okay, fine, let's change it to a minus just to change it up, because the last one was a plus. Okay, where is this continuous? The minus doesn't matter really. It's basically the same idea. So you're going to start off like this. You're going to say sine inverse is an inverse trig function. And the last example, the last result said that it's continuous on its domain. I'm not going to have room here to draw the graph, but if you can remember what the graph of sine inverse looks like, the domain was -1 to 1 with brackets like this. Okay, so please go look at a graph if you're like, where'd that come from? Okay, so that takes care of the sine inverse part. Then what about square root of x? Square root of x is algebraic, or you can just call it a root function, but let me go ahead and write algebraic. So it's continuous on its domain, which is 0 to infinity. Okay, but here's the problem. Square root of x is continuous at numbers that sine inverse isn't continuous at. Like, for example, square root of x is continuous at the number, 25, but sine inverse is not even defined at 25. So what you want to do now is, since the function we're talking about is g, where you subtract them, you want to look for what's in common to both. So let me write this down. Sine inverse is continuous. I'm basically trying to figure out what the intersection of these two sets are, or another way to say it is where they overlap. What are the numbers where they're both continuous? So the overlap for those sets is 0 to 1. Sine inverse is continuous on interval 0 to 1. If you're like, where'd you get the 0 to 1? Okay, then let me draw a picture real quick. It's like this. I'm going to look at negative 1 to 1, which is where sine inverse is continuous. And then I'm going to look at 0 to infinity, where square root of x is continuous. And I'm looking for the part that's shaded both red and blue, because I need them both to be continuous. And that gives me this 0 to 1 right here. That's the place where they're both continuous. So because sine inverse is continuous on negative 1 to 1, it's definitely continuous on 0 to 1, because that's less numbers. Also, because square root of x is continuous on, since square root of x is continuous on 0 to infinity, it's going to be continuous on 0 to 1, because that's less numbers. That's where they intersect. Okay, so sine inverse is continuous on 0 to 1. Square root of x is continuous on 0 to 1. So if you subtract them, is continuous on 0 to 1. Oh, did I just write 0 to 1? Sine inverse x minus root x, when you subtract the functions, is continuous on 0 to 1. And 0 to 1 should make sense as the, I mean, when I ask you where is it continuous, I want to get all the numbers where it's continuous. And it's clear that it can't be more than 0 to 1, because if you throw in any other numbers, besides this closed interval 0 to 1, any other numbers, there's going to be a number in there where one of them is not continuous. So again, you kind of think of a numbered line and think of where they overlap. And the overlap is where they can have a chance, where they're both continuous, so then when I subtract, I can get them to be continuous. Okay, that was fun. Let's go ahead and do a third one. Okay, so one last one here. Let's say, let's do this question. So where is let's look at the function sine x over x continuous. So again, this is not an algebraic function, a rational expression, a trig function. I know there's a trig function in there, but it's built from a trig function and a polynomial. Think of it as we got a trig function up here, polynomial down here, and we're dividing them. So we're going to use this dividing rule. Okay, so you're going to go like this. Sine, we're just going to look at the individual pieces. Sine is continuous on its domain because it's a trig function. So it's continuous on negative infinity to infinity because the domain of sine is negative infinity to infinity. Then you look at x. X is continuous on its domain. What kind of function is it? That's a polynomial. Polynomials are continuous on their domain. That's negative infinity to infinity. So if you divide them, this is continuous on the same interval, except where you get division by 0, except numbers that cause division by 0. And what numbers would cause division by 0? In other words, what numbers could you plug into this and get division by 0? Only 0. If you plug in 0, you get division by 0 down there. So this is not the answer. I have to throw out 0. So it's that answer, and then you throw out 0. Okay, so I'm going to have to erase some stuff here. Maybe I can squeeze it in up here. It's a little sloppy, but that way I don't have to erase anything. So I'm going to write it over here. So this function, sine x over x, is continuous on, got to throw out 0, negative infinity to 0, union 0 to infinity. Wow, that's really small. Okay, let me write it here. These are all parentheses just to make sure we're clear, no brackets. Union 0 to infinity. Okay, so you just basically throw out 0. And that is the answer to that one. Okay, so one more time. If it's just a polynomial, just an algebraic expression, just a rational expression, just a trig function, just an inverse trig function, just a log function, or just an exponential function, the previous result says it's continuous. The function will be continuous on its domain. Otherwise, if it's more complicated, if it's built out of those things, then you have to use this result and some kind of argument to figure out where they're continuous. If it's built of a lot of pieces, you want to find, basically you want to find the domain of each piece and figure out where they overlap, so you can figure out where they're all continuous. But you have to go ahead and quote these results. Hey, it's a trig, so I know it's continuous on its domain. Hey, it's a polynomial, I know it's continuous on its domain. Oh, we're adding them? Okay, find the domain of each one and find where they intersect, and that's where they're continuous. If you're dividing, make sure you also throw out the numbers that cause division by 0. Okay, so I hope you got comfortable with this result. Now what I want to do is I want to just real quickly prove one of them to you. So right here it says, prove that if f and g are continuous at a, then f plus g is continuous at a. So of the 5 results, I'm going to prove just the first one. Okay, I'm doing this for a couple of reasons. One reason is that it's important as far as the story goes. You know, it's part of the story. Another reason is it's going to be a good example of seeing limit laws. And the third thing is I don't want to just give you results, theorems, and say, here they are, believe them. You know, every once in a while I want to show you where they came from. It came from stuff we already know. It came from limit laws. So we'll see. Okay, so I'm going to move the theorem out of the way and just get this example up here so I have more room. Prove that if f and g are continuous at a, then f plus g is continuous at a. Okay, well, look, let's see what we're given here first. We're given that f and g are continuous at a. So if f is continuous at a, f is continuous at a, what that means, well, it means 3 things. First, it means the limit as x goes to a of f of x exists. In other words, you can take the limit as x goes to a of f of x and it exists. Then f of a exists, meaning you can plug the number a into f and it exists. And the third thing is that the limit as x goes to a of f of x exists. I'm sorry, that equals f of a. Okay, so f being continuous at a means those 3 things. We're also given that g is continuous at a. So what does that mean? So g is continuous at a means that the limit as x goes to a of g of x exists. G of a exists. And that the limit answer and the g of a answer are the same. The limit as x goes to a of g of x equals g of a. Okay, so this is what we're given. Okay, so we're given that f is continuous at a and g is continuous at a. So all this right here is given. And so now we want to prove that f plus g is continuous at a. All right, so how are we going to prove that? We're going to prove it the way we always do. We're going to go through the 3 steps. So I'm going to ask 3 questions. First question. Does the limit as x goes to a of f plus g of x exist? It may look a little confusing the way I wrote that. So let me just put a little note on the side here real quick. When you see it like this, this is basically what we're talking about. Whatever's in the parentheses is the name of the new function. So f is one function, g is another function, and the name of this new function is f plus g. And when I put an x here, x stands for the input. But when you plug in a number to f plus g to this new function, what do? You basically plug it into each thing. So this is equal to f of x plus g of x. In the second line right here, Basically what that means is if you know the formula for f and you know the formula for g, to get the formula for this new f plus g, you just take the formula for each one and you add them. So the first way up here, this is kind of like the name of the new function, but then this is kind of like how the function works. It's f of x plus g of x. So basically I'm going to be interchanging them is what I mean here. So when I go to find if this limit exists, okay, I'm going to go ahead and calculate this limit. So limit as x goes to a of f plus g. So you write it like this. This limit as x goes to a of f of x plus g of x. Okay, now, does this limit exist? Well, we have a limit law that says when you're taking the limit of a sum, you can take the limit of each thing separately as long as each individual limit exists. But each individual limit does exist. See right here, we have the limit of a exists. The limit as x goes to a of f exists. The limit of f exists. And here we have the limit as x goes to a of g exists. Those are both given. Since they both exist, we can use the limit law to find this limit as x goes to a of f plus g. It's equal to limit as x goes to a of f plus limit as x goes to a of g. And because each of these exists, so this exists, that means it's a number. This exists, that's another number. So they have two numbers we're adding, so you get a number. So exists. So the answer to the first question is yes. The limit as x goes to a of f plus g exists. And in fact, we know the answer. Let me try to squeeze the answer in over here. Because the limit as x goes to a, right here, we know the answer is f of a. So that's f of a. And the limit as x goes to a of g, we know the answer to that, it's g of a. So the limit does exist, and it's also equal to f of a plus g of a. So now we've answered the first question. The limit does exist. Okay, I'm going to have to erase here before we answer the second question. Okay, so the second thing we're going to check is does f plus g, can we plug in a to this function f plus g? Does f plus g of a exist? Well, as I said before, what this means, if you want to plug in a number to this new function, the way this function works is you plug in a to f and you plug in a to g. So you're allowed to plug into f plus g of a if you're allowed to plug in to a. You're allowed to plug in a into f plus g if you're allowed to plug it into f, which we are. It says f of a exists here. And you're allowed to plug it into g because it says g of a exists. That means this is a number and this is a number and you can add them. So that means this is going to exist. So the answer is yes to this. Let me erase this circles here. So the answer is yes. The answer is f of a plus g of a. So yes. Okay, and the third question. The third question is, does the limit answer for f plus g and the answer you get when you plug in a to f plus g, are they the same? So does the limit as x goes to a of f plus g of x equal f plus g of a? And the answer is yes, because this here, the answer, we not only said that that exists, but we said the answer to this was f of a plus g of a. Go back and look at when I put a 1 over here. Then we did f plus g of a, this part, and the answer again was f of a plus g of a. So they are equal. So yes. Okay, so the answer to all three questions about f plus g was yes. So let me just write it over here. So f plus g is continuous at a. And all the other results having to do with subtracting, dividing, multiplying are proved basically the same way. Okay, so that's how that result goes. So make sure you know the results because we're going to use it a lot. Actually, we're going to use it in this next example now. So let's go ahead and look at example 7. Okay, this example or examples similar to this are examples that I like to put on quizzes and exams. So let's make sure you understand this. What I'm doing is I'm giving you a piecewise function here. Piecewise functions are more interesting when it comes to continuity because otherwise almost every function that I give you, or I just give you one little formula, is basically continuous on its domain. Either it's directly from a result or you can make a quick little argument and say, oh, we're adding some stuff, so it's continuous on its domain. But piecewise functions are a little bit different. Okay. So basically this question is asking you, where is this function continuous? Find all the places where it's continuous. Part A is asking you about 1. It's saying, what's going on at 1? Is it continuous at 1? If it's not, is it continuous from the left or right? Part B is asking you about the number 4. Is this function fully continuous at 4? If not, is it continuous from the left or the right? And then part C says, where is this function continuous? Now, on an exam or a quiz, I don't really have to ask you part A or B. I can just go straight to part C and say, where is the function continuous? In either case, you're going to have to do a separate calculation for the number 1 and for the number 4. The numbers that appear over here, you need to handle them separately. The reason is because if I want to know what's happening at 1, if it's continuous at 1, fully continuous, or whatever, well, the piece you use depends on what side of 1 you're on. If you're on the left of 1, you use this piece. If you're on the right of 1, you use this piece. That's why you have to deal with 1 separately, because you change pieces depending on what side of 1 you're on. Same thing with 2. I'm sorry, same thing with 4. If you're trying to figure out what's happening at 4, well, if you're on the left of 4, this is the piece that you use. If you're on the right of 4, this is the piece that you use. So the piece you use depends on what side of 4 you're on. So for that reason, you're going to have to do the number 4 separately. So the way it's going to work is you're going to figure out what's happening at 1, whether it's fully continuous, continuous from the left, continuous from the right, or none of those. Then you're going to figure out what's happening at 4. Is it continuous from the left, continuous from the right, fully continuous, or none of those? And then we're going to make up some kind of argument using the results that I already gave you to figure out what's happening at all the other numbers and hope that at all the other numbers it's continuous. So, okay, so let's go ahead and get started. Let's do 1 first. Let's move this up here to give us more room. So first I'm worrying about the number 1. So at x equal 1, what's going on? Okay, so first question for continuity, does the limit as x goes to 1 of this function exist? So to figure that out, remember, to find this limit, we talked about limits of piecewise functions, and when you're trying to find the limit as x goes to 1, since the piece you use depends on what side of 1 you're on, you're going to have to use left and right hand limits for this limit. So let's see, let's do limit as x goes to 1 from the left of the function. Well, since we're on the left of the function, that means our inputs are less than 1. So we're going to use the top piece when we're finding the limit, x squared minus 7. Now it's pretty easy to find the limit of that because it's just the limit of a polynomial. So you can plug in and you get 1 squared minus 7. So you get negative 6. Okay. Then you do the limit as x goes to 1 from the right of the function. Since we're on the right of 1, but close to 1, you have to use this piece when you're finding the limit. Limit as x goes to 1 from the right of 2x minus 6. Again, you can just plug into this because it's a polynomial. So you get negative 4, it looks like. All right, so this first question is already no. Does the limit exist? No. Even though the limit doesn't exist, though, that doesn't mean it's not continuous from the left or right. So we do have to keep going. But does everyone agree the full limit doesn't exist? It doesn't exist because the left and right hand limits are different. Okay, let's go to the second part. The second part you would ask yourself is, does g of 1 exist? In other words, can you plug in 1 to the function? Well, when you go to plug in 1, you would use the middle piece. Because the middle piece here, where it says x is greater than or equal to 1, x could be equal to 1. So that's when you use the middle piece. Okay, so to find g of 1, you plug into the middle piece. But you get negative 4. So the answer is yes to this. G of 1 exists. Okay, now if you compare this negative 4 answer here to the answers over here, you see that this -4 equals this -4. This -4 was the right-hand limit. So even though I know it's not fully continuous because the answer to this first question was no, it looks like it's going to be continuous from the right because the right-hand limit is equaling g of 1. So the third question, I'm going to have to erase some stuff, I apologize, but let's do the third question. Okay, so the third question, does the limit as x goes to 1, we're going to make it a right-hand limit now, because otherwise we know the full limit doesn't exist. Does the limit as x goes to 1 from the right of g of x equal g of 1? And the answer is yes, because we calculated those. I just erased them, I know. But this answer was, what was it? It was -4. And this answer was also -4. So the answer is yes. So what have I learned? So g is continuous from the right at x equal 1. Okay, so now we know what's happening at 1. It's not fully continuous, but g is continuous from the right at 1. Okay, now we have to ask those same 3 questions again when it comes to the number 4 and see if it's continuous at 4. From the left, from the right, fully continuous, or what? Okay, so let's check out 4. Okay, so we're focusing on the number 4 now. And again, ask the same 3 questions. First question, does the limit as x goes to 4 of g of x exists? Once again, to know which piece to take the limit of, it depends on what side of 4 you're on. That means we're going to have to do left and right hand limits. So we'll do limit as x goes to 4 from the left. And when you're on the left of 4, that means you're less than 4. If you're less than 4, use the middle piece. So we're taking the limit of 2x minus 6. Once again, a polynomial. So you can go ahead and plug in. And you get 2 times 4 minus 6, which looks like it's 2. 8 minus 6, so 2. All right, then I'm going to do limit as x goes to 4 from the right of the function. And when you're on the right side of 4, use the bottom piece. So you take the limit as x goes to 4 from the right of square root of x. Okay, that's an algebraic expression you can plug in as long as you don't get 0 inside of an even root, a negative number inside of an even root, or division by 0. You don't get any of those things when you plug in. You just get square root of 4. No problem. You get 2 again. Okay, cool. So the left and right hand limit both exist. So the full limit exists. So limit as x goes to 4, full limit turns out to be 2. Okay, so the answer is yes to this question. The full limit exists, and it's 2. All right, let's go to the second part. So the second question is, does g of 4 exist? In other words, can you plug in 4 to this function? And the answer is yes. G of 4, when you're going to plug in 4, it says if your input is greater than or equal to 4, if it's equal to 4, you plug it in here. So you're going to plug it in there, you get square root of 4, which is 2. So yes, you can plug in 4 and you get an answer, and the answer is 2. Okay, third question you're going to ask, does the limit answer that you got in number 1, limit as x goes to 4 of g, does that equal g of 4? And the answer to that is yes, because we calculated them both. This limit was 2 and g of 4 was 2. Yes, they're equal. Okay, so the answer to all 3 questions is yes. So what's the conclusion? So g is fully continuous at x equal 4. So at this point, I know what's happening at 1, and I know what's happening at 4. At 1, it's continuous from the right, and at 4, it's fully continuous. Now, think of all the other numbers that there are on the number line. There's still infinitely many numbers. What I want to do is I want to know, what about all the rest of the numbers? Is this function continuous at all the rest of the numbers? But you see, I don't want to just pick one number at a time. I don't want to be like, okay, let's see if it's continuous at 7. Let's see if it's continuous at 3. Let's see if it's continuous at -2. That'll take me forever. I don't want to go through this 3-step process forever. So now the idea is we're going to kind of make some kind of argument, and I'm going to show you how you can prove from the results we already talked about that this function is continuous basically everywhere else. So let me go ahead and draw a number line real quick so we can get an idea of what I'm thinking about here. Okay, so here's a number line. And we just figured out what's going on at 1. We figured out what's going on at 4. Let me go ahead and just write that down here, that it's fully continuous here. And here it's continuous from the right. I'll just write right. Okay, so we took care of these two numbers. I know what's happening at 1. I know what's happening at 4. But now what I want to know is what's happening at all these numbers, then what's happening at all these numbers, then what's happening at all these numbers. Okay, so the formula for the function depends on which of these three segments you're on. So I'm going to go one segment at a time and argue that the function is continuous there. So it's going to go like this. So now, on the interval -infinity to 1, so I'm talking about all these numbers here, up to 1. Don't include 1. We already talked about 1, so don't mention 1. From -infinity to 1, what's going on? On that interval, the formula for the function g of x, if you're on the interval -infinity to 1, that means you're less than 1. This is the formula for the function. It's this, and what do you know about it? So g, the function I'm trying to talk about, is a polynomial. And what do you know about polynomials? So it's continuous everywhere. Polynomials are continuous everywhere. But of course, g is only the polynomial from -infinity to 1, so I can only really talk about -infinity to 1. So g is continuous on -infinity to 1. And maybe I should write fully continuous here. It's fully continuous. Okay, so now I just figured out what's happening at all these numbers. It's fully continuous at all those numbers. Fully continuous. Before we continue, I just want to put a little warning out there. If this wasn't a polynomial, if this was something that could be undefined, if there's any numbers in this segment here where you get undefined, then you of course have to throw those out. Can't be continuous there. But anyway, it's a polynomial, no problems, continuous at all those numbers. Okay, so we just made an argument about these numbers, continuous at all these. Now we're going to look at these numbers over here in the middle, between 1 and 4. So make another argument like that. Okay, so now we're going to say what's going on the interval 1 to 4. Now, some people get confused. They put a bracket here on the 1. They'll put a bracket here because they see a less than or equal to here. Definitely don't do that, because when it comes to 1, well, number 1, we already dealt with 1, so you really don't have to do it. Also, if you put the bracket there, you might make mistakes. So long story short, let's just always use parentheses for the rest of these. We took care of 1, so don't talk about 1 anymore. We took care of 4, don't talk about 4 anymore. Now also remember that it's g that we're talking about, so I don't want you to write down 2x minus 6, I want you to write down g. But the formula for g is 2x minus 6 if we're on this interval here. Okay, so g of x is 2x minus 6. This is also a polynomial. So the polynomial is continuous everywhere. But again, the polynomial is not g. The polynomial is only equal to g on this interval. So I'm going to say, so g is continuous. Fully continuous. Let me write fully continuous. Fully continuous on the interval 1 to 4. So just because it's a polynomial, it's continuous everywhere, but again, it's not the polynomial that I want to talk about, it's g that I want to talk about. G is only equal to that polynomial between 1 and 4. So that's how I know g is continuous between 1 and 4. And now we just dealt with all these numbers. I know that it's fully continuous at all these numbers, took care of them all. So last we're going to look at these numbers. What's going on there? So we'll make one more argument like that. Okay, so we're going to write on, so what number is bigger than 4? So you're going to write 4 to infinity. Again, put a parentheses. I know you see, let's erase some of this. I know you see a greater than or equal to right here. Okay, but even though it says equal to, don't deal with 4. We've already dealt with 4. We already know what's going on at 4. So I only want to know about the numbers bigger than 4. On the interval 4 to infinity, you can tell me what the formula for g is. The formula for g is square root of x, which is algebraic. Or you can write which is a root function, either one. So it's continuous on its domain, which is 0 to infinity. So this is continuous on 0 to infinity, but g is what I want to talk about. So g is only equal to the square root of x on this interval, but this interval is contained inside here, right? Because if you look at the picture, the number line picture, here's 4 to infinity right here, but 0 to infinity is like, more stuff. Okay, so since I know that square root of x is continuous on 0 to infinity, square root of x is definitely continuous on 4 to infinity, and that's when it's equal to g. So g is continuous. Again, I forgot to write fully. Is fully continuous on the interval 4 to infinity. Okay, so you quote some results that we've used, and that one's fully continuous from 4 to infinity. Now I know what's happening at all these numbers, and now I've taken care of every number there is. I know what's happening everywhere. One more time, let me warn you over here. This square root of x, you know it's not continuous at negative numbers. So if there would have been any negative numbers in this last range over here, there aren't, but if there were, you need to throw them out. Or sometimes on quizzes I'll put something like this, where maybe you have like, instead of square root of x, you'll have like a 1 over x here. Okay, on this interval, 1 over 4 to infinity, 1 over x will be continuous the whole time, because the only problem with 1 over x is when x is 0, you get division by 0. But if this would have said negative 4 here, then 0 is in this range here, you'd have to throw it out. I guess you have to make some kind of argument like that. So you'd do this kind of argument that we just did, except you'd say, okay, 4 to infinity, except you have to throw out 0. Okay, so let's write down the final answer to this problem now. Basically, remember what we figured out is that f is fully continuous at all these numbers, fully continuous at all these numbers, fully continuous at all these numbers, even fully continuous at negative 4. And there was just one issue here, and the issue here was at 1, it's only continuous from the right. Okay, so let's write that answer down. So, I'm sorry, I might have said f, but anyway, g. So g is continuous on, you don't have to break it up into pieces, because since it's continuous, since it's fully continuous here and here and here, you can put that all in one big mess. It's just the one where you have to do something to show me that it's only continuous from the right. So you're going to go negative infinity to 1, and you're going to put parentheses on negative infinity, parentheses on the 1, because if you put a bracket on the 1, it would mean it's continuous from the left at 1, and it's not. Union, and then you're going to go 1 to infinity. Again, you don't have to stop at 4, because it's continuous from 1, from bigger than 1 on, 4 included and past 4. But at the 1, you have to put a bracket. And the bracket just means it's continuous from the right at 1. Okay, so that's the answer. And that is the end of the video. So I hope this lecture made sense. Go over it a lot. Make sure you get everything. Continuity is not the easiest topic. That's why I wanted to go over it slow, put a lot of videos out there. But please go over it, be really good at it, and I will see you next class. Study hard, guys.